Chapter 2b, Heat, Internal Energy, and Enthalpy. In the last section, we learned how to calculate work. So here are some important special cases that you need to remember. Constant volume, constant pressure, reversible, and constant temperature. So whenever volume is constant, work is zero. When pressure is constant, work can calculate simply by negative pressure times volume change. If it's reversible and constant temperature, work is calculated by negative nRT ln V2 over V1. So now the question is, how do we calculate heat? We use heat capacity to calculate heat. Heat capacity, C, is defined as the amount of heat required to raise temperature of substance by 1 degree, okay? 1 degree Celsius or Kelvin, because 1 Celsius is 1 Kelvin, the same. So we can write as Q divided by T or dQ divided by dt. So that's the heat capacity, which means joule per second. Okay. Now let's think about another concept, the speed. Speed is distance over time. So it's meter per second. Every second, how many meters it go. So that's the speed. So if we know speed, we can calculate the distance. Distance is speed times time per second. Meter per second times seconds. That gives you how many meters, okay, how long it runs. So that's the distance. So similarly, heat capacity is heat per temperature, so joule per seconds. So if we know heat capacity, we can calculate the heat. So heat can be calculated by heat capacity times temperature. So joule per second per Kelvin times Kelvin. How much temperature change? Now, if heat capacity is a constant, okay, we can use this one. If heat capacity is not constant, we can only use a small temperature change times heat capacity, give you a small heat change. And so the heat should be calculated by integration heat change. So that's when heat capacity changes. But usually heat capacity is a constant. So we can rewrite as Q equals heat capacity times temperature change. As we know, both work and heat are non-state function that depends on path, and therefore different paths have different heat capacity. For example, when volume is constant, the heat capacity is called constant volume heat capacity. So this represents constant volume heat capacity. So a constant volume heat is calculated by constant volume heat capacity times temperature. Now, if the process is a constant pressure, then the heat capacity is written as Cp. P means constant pressure. So that is how much heat you need to raise temperature 1 degree at a constant pressure. So the heat under constant pressure is calculated by Cp delta T, constant pressure heat capacity times temperature change. An example of constant volume process is bomb calorimeter. So this is a reactor made of stainless steel, and a gas phase reaction takes place inside this stainless steel reactor. And because volume does not change, work must be zero. All right. And the first law says delta U equals Q plus W, but W is zero. Okay, this is zero. So delta U equals Q. V means constant volume. So constant volume heat equals internal energy. Constant volume heat equals internal energy. And this comes from first law of thermodynamics. Therefore, this applies to any gas, ideal, non-ideal. Internal energy change equals Q under constant volume. We just showed that as long as volume is constant, work is 0, and delta U equals Q. Okay, so this is constant volume heat equals delta U. Now, usually Q is a non-state function. However, this equation says that on the constant volume, heat is related to a state function delta U. And therefore, this allows us to calculate heat capacity using internal energy change, a state function. And so, because heat capacity is defined as dQ over dt, so how much heat needed to increase temperature 1 degree. But the constant volume dQ equals du, and therefore heat capacity is du over dt. Okay, so that's the state function change with temperature. Now, usually internal energy is a function not only temperature but also volume, okay, other variables. And so in calculus, this kind of function derivative only over temperature is called a partial derivative. So this is partial derivative of internal energy over temperature when volume is constant. So this means keep volume constant, only change temperature, and the derivative of internal energy change over temperature. That's the constant volume heat capacity. Because internal energy is a state function, so we know how internal energy change theoretically. So we can calculate internal energy change over temperature. So this is how internal energy change with temperature is a curve shows how internal energy change with temperature. And at any instant, the slope tells you the heat capacity, the derivative of internal energy. That's the slope that tells you the heat capacity. So remember in Chapter 1b for gas phase, the average kinetic energy, okay, for one molecule, is 3/2 kT, right? So for one mole, the kinetic energy is 3/2 RT. Now, if it's ideal gas, then there's no potential energy, and that would be internal energy. So average internal energy for one mole ideal gas is 3/2 RT. So based on here, this equation, we can calculate heat capacity for ideal gas will be the derivative of 3/2 RT over temperature. Okay, so in calculus, we know a constant times x derivative is just a constant. So this one, the variable is temperature. Derivative over temperature will give you 3/2 R. That's the theoretical prediction for heat capacity of ideal gas is 3/2 R. All right. Now this equation is applies to monatomic ideal gas. For example, argon, helium, neon, these monatomic gas. For diatomic nitrogen, okay, or oxygen, or any molecules more than one atom, these molecules rotate, vibrate. They need more energy when you raise temperature 1 degree. So the heat capacity will be more than 3/2 R. All right, so remember, constant volume, therefore, internal energy can be calculated by CV delta T, because CV is du over dt. So du equals CV delta T. And CV delta T is also the heat. Heat capacity times temperature change is the heat. Okay, so this equation again applies to constant volume for any gas. Let's summarize the constant volume process. As long as volume is constant, you should immediately remember the W is 0, no work is done, and according to the first law, delta U equals Q. So how do you calculate heat? under constant volume? Well, heat always calculated by heat capacity times temperature. So for constant volume, heat capacity or constant volume heat is calculated by CV delta T. Now under constant volume, delta U is also calculated by CV delta T. All right, so that's an important equation. How do you calculate internal energy? Well, constant volume, CV delta T. Okay, and the heat capacity is defined on a constant volume. Is defined as the partial derivative of internal energy over temperature on the constant volume. Okay, why internal energy? Because constant volume, internal energy change is heat. Okay, that's why. Having looked at the constant volume process, now let's move on to constant pressure process. So if pressure is constant, what we have learned? Okay, we have learned that we can calculate work. Work is negative pressure times volume change. So according to the first law, again, delta U equals Q plus W. Here, W is negative pressure times volume change. So put inside. So delta U now becomes Q minus P dV. Here, pressure means constant pressure, heat. All right, minus P dV. Rearrange this equation to calculate the heat. So we have this equation. Q equals delta U plus delta V. All right, that's another interesting equation because, again, heat usually is a non-state function. But under constant pressure, it says heat is related to delta U, which is a state function. P, that's a state function. V, that's also a state function. So heat under constant pressure, just like under constant volume, remember constant volume, heat equals delta U, that's a state function. Here, it relates to not only U, but also P and V, they are all state function. So if we combine them all together, okay, note that these are the change. So if we combine them as a function U, this function U plus P times V, because here P times delta V. And so if pressure doesn't change, so this is constant pressure, it doesn't change. So U plus PV, and that is a state function that relates to the heat change. So we define a new state function, we call it enthalpy. So enthalpy is U plus PV, okay? So why do we think about that? Because if you delta H, delta change, will be delta U plus delta PV, okay? Now because pressure is constant, so this will be just the P times delta V, because P is a constant. So delta U plus P delta V, that's delta H. And you see this delta U plus delta P delta V is just here, which is a Q. And that indicates delta H equals Q. So under constant pressure, we showed that heat is related to a new state function called enthalpy, which is a combination of U plus PV. Okay, so we have an important conclusion. All right, both constant volume and constant pressure process, heat are related to state function. Constant volume, delta Q is related to internal energy change, but the constant pressure, heat is related to a state function called enthalpy change. We just showed that under constant pressure, heat is related to a new state function delta H. And therefore, we can also calculate the heat capacity using enthalpy change. Just like constant volume, we use internal energy. Okay, remember CV is partial derivative of internal energy over temperature under constant volume. Because constant volume, U, delta U equals Q. Okay, dQ. Same thing is here, all right? And when constant pressure, delta H equals dQ, is the heat. So Q divided by T, that's the heat capacity. Okay, again, it's a state function. So if we know how enthalpy change, the derivative, the slope, give you Cp at any instant. If heat capacity is a constant, we can simply write as Cp delta T. Okay, so according to this equation, Cp delta T give you delta H. Now, if heat capacity is not a constant change with time, then you need to integrate. All right, so this is valid for any process at any pressure. Let's summarize the constant pressure process. As long as the pressure is constant, you should immediately remember work can be calculated by negative pressure times volume change. Heat is always calculated by heat capacity times temperature change. For constant pressure, you need to use the constant pressure, Cp, constant pressure heat capacity times temperature change. And we just show that on the constant pressure, there's a new state function, H equals U plus PV, that's a enthalpy that relates to heat. So the heat on the constant pressure equals the new state function change delta H, which both equals Cp delta T. Okay, and on the constant pressure, therefore we can calculate the heat capacity by enthalpy derivative over temperature under constant pressure. We have learned that internal energy change can be calculated under constant volume, which equals Q, which can be calculated by Cv delta T. So this equation is valid for any gas. We can always calculate internal energy change if volume is constant. But what if volume changes? Well, let's first look at ideal gas. Okay, so the internal energy is the sum of kinetic energy plus potential energy. Kinetic energy is a measure of motion, how fast it goes. For example, physics says half mv squared. So it's related to motion. Potential energy is related to position, okay, intermolecular interaction. And for ideal gas, well, there's no intermolecular interaction, and therefore potential energy is zero. And so the internal energy is only related to kinetic energy. And we already know kinetic energy is determined by temperature. In the gas phase is 3/2 RT, okay, for average kinetic energy. So therefore, we have an important conclusion that for ideal gas, internal energy is a function of temperature only. As long as you know the temperature change, you can calculate internal energy change for ideal gas. We just showed that internal energy is a function of temperature. And so we can calculate internal energy if we know temperature change. Now let's assume a change from initial temperature T1 to T2. And this can go along several different paths. So path 1A, path B, path C, okay, so different paths. So how do we calculate delta U? They all should have the same delta U because it's state function. So no matter how you go there, they have the same delta U. But how do you know that? How do you calculate? We want to choose a path that we can calculate. So this path can be constant pressure, constant volume, or any process. But what we choose is the constant volume, because on the constant volume, we can calculate delta U. All right. So constant if volume is constant, work is zero, and therefore delta U equals Q. So, and Q is Cv delta T. And therefore, even though you can go from initial state to final state with many different paths, we choose constant volume because that's the path we can calculate, and all paths should give you the same delta U, because internal energy is a state function, only depends on T1 and T2. And this is the equation. This equation is derived from constant volume, but here it also applies to all other processes. It can be constant pressure. As long as temperature change is the same, delta U is the same. So delta U CV delta T, always true for ideal gas. Okay, only for ideal gas. You can always use CV delta T. Okay, that's a very important conclusion. Now, we learned that CV, heat capacity, is designed to calculate heat. So is this heat, CV delta T? Well, this is heat only constant volume. So constant volume, this will be heat. If it's constant pressure, CV delta T is not heat, because constant pressure, it should be CP delta T. Okay, that will be heat for constant pressure. However, even for constant pressure, internal energy is still CV delta T. Okay, that's a very important conclusion. For ideal gas, internal energy is a function of temperature only. The equation is CV delta T. Okay, always this equation. We just showed that for ideal gas, internal energy change can always calculate by CV delta T. Now, what about non-ideal gas? How do we calculate internal energy change? Well, let's look at a diagram that the system goes from initial state V1 T1 to final state V2 T2. Okay, so how do you calculate the internal change for this process? Well, remember, internal energy is a state function that only depends on initial state, final state. That means we can go a different path. All right, so let's go first horizontally. So in this diagram, horizontal means constant volume. Okay, because that's the volume. So constant volume go from T1 to T2. All right, and then vertically, all right, from V1 to V2, change volume. Okay, constant temperature, because this is the temperature. So vertical means constant temperature. Okay, so if we can calculate internal energy for each of these steps, delta U1, delta U2, add together will give you the total internal energy, because state function doesn't depend on path. All right, so how do we calculate delta U1, the first step, which is a constant volume? Well, we are familiar with constant volume because work is zero, so delta U is heat, which is CV delta T. So first step, we can easily calculate. Even if it's non-ideal gas, that's true. Okay, but for the second step, when temperature is constant, all right. So if it's ideal gas, if temperature is constant, then internal energy shouldn't change, because for ideal gas is 3/2 RT. Remember, the internal energy is 3/2. So only depends on temperature. There's no potential energy. So for ideal gas, if temperature is constant, internal energy doesn't change. However, if it's non-ideal gas, when you change volume, the internal energy also change. And in calculus, we can write as the derivative of internal energy over volume. That means how fast internal energy change with volume, and then times volume. So the total internal energy change for these two steps, from T1 V1 to T2 V2, you add these two together. One is due to the constant volume, so this is a constant volume, and this is a constant temperature. All right. Now, usually this is a very small number, but it may not be zero for non-ideal gas. But if it's an ideal gas, then constant temperature, internal energy shouldn't change. So the second step will be zero. and therefore internal energy is only the first step, CV delta T. So again, we showed that for ideal gas, internal energy is always CV delta T. For non-ideal gas, you need to add another term that show how internal energy change with volume. Let's think about what CV delta T represent. So first, heat capacity is used to calculate heat, and therefore CV delta T is to calculate heat only under constant volume, because this is a constant volume heat capacity. All right. Second, if volume is constant, work is 0, then heat equals delta U. So CV delta T equals delta U for constant volume. Okay. Now this applies to all gases. Okay, all gases, because this comes from the first law of thermodynamics. So apply to all gases, as long as constant volume, delta U equals CV delta T. What about what about ideal gas? So this is for all gas. What about ideal gas? If it's ideal gas, then internal energy does not change with volume, because there's no intermolecular interaction. Internal energy is a function of temperature only. So here, this equation about temperature change applies to all process. So it is for ideal gas or process. Okay, it can be constant volume or constant pressure or isothermal expansion. So all process, you can always use delta U equals CV delta T, but must be ideal gas. Okay, because ideal gas internal energy is a function of temperature only. So you can always use CV delta T to calculate delta U. But if it's not ideal gas, okay, if it's not ideal gas, then CV delta T equals delta U only apply for constant volume. Okay, if volume is constant, that's still true. Delta U equals CV delta T. It can be non-ideal gas. Here's a sample question that you already seen before. Ask you to calculate work. Okay, so but now we are going to calculate not only work but also internal energy and heat. We already showed how to calculate work. All right. So for constant pressure, negative pressure times volume change. For constant volume, work is 0. And for isothermal reversible, it's negative nRT ln final over initial. All right. So I hope at this point you should be familiar with the equations to calculate work. Now, how do you calculate heat and internal energy change? Well, let's start with constant volume. So if volume is constant, work heat equals internal energy change. Both are calculated by CV delta T. Okay. Now sometimes you may you don't need you don't have temperature, and you have to use ideal gas law to solve temperature first. And for example, here you have pressure, volume, and here you can also find the pressure, volume, and you have a number of moles. So it's a typical question in chapter 2 that sometimes you need to use equations learned from chapter 1 to calculate the state, the temperature, the pressure, the volume, so that you can calculate heat, internal energy change, and work. All right, so what about constant pressure process? Well, constant pressure, you can still use CV delta T. Remember, if it's ideal gas, okay? As long as it's ideal gas, you can always use CV delta T, but you need to calculate temperature. So T1, calculate temperature T1, calculate temperature T2. All right, so I suggest you try it, and CV delta T, you will get 99.6 kilojoule per mole. Now, I want to explain the difference CV and the CVM. So here it says CVM 20.79. So CVM is the heat capacity, constant volume heat capacity per mole. So CV is the total heat capacity of constant volume. So it's N times CVM. Okay, so sometimes we write delta U equals CV delta T, but more commonly it's N CVM times delta T, because this is molar heat capacity. You times total number of moles. All right, that gives you total heat capacity. All right, so that's delta U. Now, how do you calculate the heat? All right, so calculate heat, we can, for constant pressure, you can use Cp delta T, but Cp is not given. Now, in the future, we can derive equation, so we can calculate the Cp, but at this point, we don't know. So, is there a way we can calculate the heat? Well, don't forget the first law. We'll have W, we already have delta U, and therefore, we can calculate heat from the first law. Okay, so Q equals delta U minus W, so you can calculate. Okay, and for isothermal expansion, you can still use delta U equals CV delta T. So remember, CV delta T always true if it's ideal gas. So isothermal still CV delta T, but delta T 0 because it's isothermal, constant temperature. As long as the temperature is constant, delta T 0, delta U will be 0. And then use the first law. So Q will be negative W, and W is calculated. Okay, similarly, constant pressure Q can be calculated. Let's compare internal energy and enthalpy. Internal energy is the sum of kinetic energy, potential energy. It's fundamental to the system. Enthalpy is more commonly used for convenience to calculate the heat under constant pressure. Enthalpy is defined as internal energy plus PV. So if it's ideal gas, we have learned that ideal gas internal energy only depends on kinetic energy, which is a function of temperature only. Potential energy is 0 because there's no intermolecular interaction. So what about enthalpy? So enthalpy is a function, or is internal energy plus PV, but internal energy is a function of temperature only. PV for ideal gas is nRT. Therefore, it's also a function of temperature only. So both internal energy and the PV are function of temperature only, and therefore enthalpy is also a function of temperature only for ideal gas. How do we calculate enthalpy change? Suppose we have a change from initial temperature T1 to final temperature T2, and it can go along different paths. Let's say path A, path B, path C, all right? And we know that enthalpy is a state function, so as long as initial final has the same initial final state, they should give you same delta H, and therefore we need to choose a path that we can calculate. Just when we calculate delta U, remember when we calculate delta U, we choose the constant volume, because on the constant volume, delta U equals Q. Okay, and therefore, which equals CV delta T. So delta U equals CV delta T for constant volume, but then it applies to any other process as long as it is ideal gas. Same thing is here. We need to choose a path we can calculate delta H, and that path is constant pressure. Okay, so if you remember, under constant pressure, we showed that the heat is related to an enthalpy change, a new state function called enthalpy. So therefore, delta H equals Cp delta T. All right, because constant pressure, heat is Cp delta T. Now, in the last slide, we showed that enthalpy is a function of temperature only, and therefore, as long as you have a change, initial state is T1, final state is T2. Okay, whether it's a constant volume, constant pressure, as long as they have same constant initial temperature, final temperature, the equation to calculate enthalpy is the same. Delta H equals Cp delta T for ideal gas. Okay, always true. Just like this equation to calculate the internal energy, always Cv delta T as long as it's ideal gas. But is this heat? Okay, not always. It is heat only when it is constant pressure. So constant pressure, Cp delta T is heat. If it's a constant volume, it's Cv delta T is heat. Okay, so constant pressure, all right, then Cp delta T is heat. But even for constant volume, okay, Cp delta T is not heat, but it's still delta H. You can calculate delta H by Cp delta T for constant volume, constant pressure for any other process. How to calculate enthalpy change for non-ideal gas? We use the same strategy to calculate internal energy. So we look at this diagram, let temperature pressure change from P1 T1 to P2 T2. And because enthalpy is a state function, so we can design a path. So let first horizontal change from T1 to T2 under constant pressure, and then under constant temperature vertically goes to final pressure. And for constant pressure, all right, because pressure is constant, enthalpy change is Cp delta T. For constant volume or temperature, all right, volume change, for a pressure change, and the enthalpy change in calculus we can written as enthalpy derivative of pressure times delta P. So the total enthalpy change is two steps: constant pressure Cp delta T, constant temperature, which is enthalpy derivative of pressure under constant pressure. All right, now we showed that if it's ideal gas, then enthalpy only depend on temperature. Pressure shouldn't affect enthalpy, so this will become 0. So if it's ideal gas, all right, and therefore for ideal gas, then delta H is always Cp delta T. But if it's not ideal gas, then you have to add this term to show how enthalpy change when pressure change, the pressure dependence of enthalpy change. Now let's think what Cp delta T represents. So first, heat capacity times temperature. This is used to calculate the heat. And heat capacity here is constant pressure heat capacity. So Cp delta T must represent heat under constant pressure. Okay, that's because of the definition of heat capacity. Now second, under constant pressure, if its pressure is constant, we show that heat equals a state function delta H, and therefore Cp delta T also equals to delta H under constant pressure. Okay, because this comes from first law, so it applies to any gas. So if it's constant pressure, then for any gas, delta H is Cp delta T. And then the last few slides, we show that if it's ideal gas, then heat enthalpy is a function of temperature only, and therefore Cp delta T now is always delta H for any process. It doesn't have to be constant pressure. It can be constant volume. Okay, it can be constant volume, can be isothermal or constant pressure. So any process, Cp delta T is always delta H if it's ideal gas. Here's a summary of delta H, delta U. For ideal gas, since there's no intermolecular interaction, so there's no potential energy, or delta U is only a function of temperature only, so it's Cv delta T. Similarly, delta H is also temperature, so depends on temperature, it's Cp delta T. Now for non-ideal gas, then an internal energy change with volume, enthalpy also change with volume or pressure, and therefore you need to add, okay, a derivative of internal energy over volume times volume change. Similarly, enthalpy, you need to add pressure dependence, okay, of enthalpy. So how do we measure in the lab? We measure when we choose volume is constant for internal energy. Okay, so when volume is constant, then the second term is 0. Okay, so this is 0, and therefore delta U must always Cv delta T. Okay, and for enthalpy, we measure under constant pressure because this becomes 0, so it's just Cp delta T. At what condition is the following equation true? When Q is delta U, well, heat equals delta U. According to first law, W must be 0, so that's constant volume. So this is true under constant volume. When can Q equals Cv delta T? Well, Cv is heat capacity under constant volume. So this is heat only when volume is constant. So again, this is for constant volume process. So when can you calculate delta U by Cv delta T? Well, if it's constant volume, heat is constant volume, work is 0, heat is delta U. So this equation must be true for ideal, for non-ideal is always true if it's constant volume. What if it's not a constant volume? If it's not constant volume, this equation is still true for ideal gas. Okay, because ideal gas internal energy is a function of temperature only. So you can always calculate delta U by Cv delta T. Okay, next, when heat equals delta H, well, we showed that under constant pressure, heat equals delta H. When can you calculate heat by Cp delta T? Well, Cp is the heat capacity under constant pressure. So this Cp delta T equals Q, only constant pressure. So both of them are constant pressure. When can you calculate delta H by Cp delta T? Well, Cp delta T is the heat. So delta H equals heat, that's constant pressure. And also, this comes from first law. So delta H equals Cp delta T if it's constant pressure for any gas, ideal, non-ideal, this is true. But if it's not a constant pressure, is this equation still valid? Yes, if it's ideal gas. Okay, if it's ideal gas, then delta H equals Cp delta T always true. It doesn't have to be constant pressure. Simple question. The molar enthalpy of vaporization of benzene at its boiling point is 30.8 kilojoule. What is the molar internal energy change? Now first, for vaporization process, the pressure is constant. So it's a constant pressure process, and therefore the vaporization enthalpy change equals heat. So constant pressure, enthalpy equals heat. So we know this process heat is 30.8 kilojoule per mole. To calculate internal energy, we can use the first law. So method 1, we use the first law of thermodynamics. Here, the heat is 30.8 kilojoule per mole, and therefore we need to calculate W. Now W is, for constant pressure, is negative pressure times volume change. And the volume change is from liquid vaporized becomes gas phase. So it's the gas volume minus liquid volume. But usually volume of liquid is much, much smaller than the gas phase. Remember, imagine one drop of liquid can become a very large volume of gas. So Vg is much greater than Vl, and therefore we can approximate just Vg. So it's just the pressure times volume of the gas. Liquid is too small, okay? And therefore, the W is just negative pressure times volume of the gas. And if we assume it's a ideal gas, okay, which usually is true under 1 atmosphere, so we have negative nRT because PV equals nRT. Okay, so that's W, and therefore delta U equals Q plus W. So plug in the Q, the W, all right, and we can get 27.9 kilojoule per mole. So you see, to solve this problem, we have several assumptions. First, we know delta H equals Q. Second, we know volume of the liquid is too small, so assumed to be 0. And ideal gas law is assumed also in this case. So that's method 1. Now in method 2, we can also use the definition of enthalpy, because enthalpy is U plus PV, so delta U H equals delta U plus P delta V. So in order to calculate delta U, we need to know delta H, which is given 30.8 kilojoules. So this is known. And what about the P delta V? So that is similar to the method 1. Delta V is the volume of the gas minus liquid, and therefore it's approximate just the volume of the gas. And then PV equals nRT. So we can use the method 2. You should get the same answer. Constant pressure heat capacity Cp, constant volume heat capacity Cv. Are they different? If so, which one is larger? In constant volume, there's no work. So heat equals internal energy, which means that all heat absorbed is to increase temperature. Under constant pressure, however, when heat is absorbed, volume expands. So it does work to the surrounding, and when it does surrounding, it needs more heat. So constant pressure needs more heat to increase temperature 1 degree, not just to increase internal energy, increase temperature, but also to work to the surrounding. And therefore, we predict that Cp is greater than Cv. But by how much? Here is the important equation. Cp minus Cv equals Nr, or Cpm minus Cvm equals R. So molar heat capacity of constant pressure is greater than molar heat capacity of constant volume by R constant. All right, so if you are given Cvm, you can calculate Cpm by Cvm plus R, okay, because Cp is greater than Cv. You need to add R constant, and that make calculation more convenient. So now let's derive this equation, okay? So why Cp minus Cv equals Nr, okay? So the Cp is defined as enthalpy change over temperature, okay? Why? Because constant pressure enthalpy change is heat. So under constant pressure, heat derivative of temperature is dH over dt, okay? Cv will be internal energy over dt under constant volume, okay? Because constant volume, internal energy, the difference is the heat. Now, what is enthalpy? So enthalpy is defined as U plus PV. And so this one is internal energy, all right, derivative over temperature under constant pressure plus PV derivative over temperature under constant pressure. Okay, because enthalpy is U plus PV, so you can separate U derivative and the PV derivative. Okay, so then you need to minus, okay, the CV, which is U derivative over T under constant volume. And if you look at the first term, compare first and the third, okay, both are internal energy derivative over temperature. One is constant pressure, one is constant volume. Now, if we are talking about the ideal gas, all right, if it's ideal gas, then pressure, volume shouldn't affect internal energy, only temperature, all right? So only internal energy is determined only by temperature, and therefore this first term, third term will be the same, because both are about internal energy change with temperature. Okay, pressure, volume do not affect internal energy, and therefore we only have PV derivative over temperature under constant pressure. But if it's ideal gas, PV equals nRT. So we are talking about the derivative of nRT over T under constant pressure. Okay. All right. So note that nR is a constant. So when you derivative, you can move out. All right. And then only temperature derivative over temperature, that cancel out. So what we get is just nR. Okay, so we proved that if it's ideal gas, Cp minus Cv equals nR. So if we divide by number of moles, then Cpm, okay, molar heat capacity constant pressure, minus Cvm should equals to R. All right, again, it's a useful equation that you will use in the future for calculations. This table compares work, heat, internal energy change, enthalpy change under special conditions. And this is a very important table. If you know how to calculate all of them, you should be fine in this chapter. So I would suggest you to work on each of them before we work together. All right. So assume now you already did each of them by yourself. So now let's go over together. All right. What is work under constant volume? Okay, constant volume, volume doesn't change, work is 0. Okay, what about the constant pressure? All right, the equation is negative pressure times volume change. Isothermal reversible equation is negative nRT ln V2 over V1. So work is path dependent. You must know the path, whether it's constant volume or constant pressure or isothermal reversible, to choose the correct equation. So how to calculate the heat? Heat is calculated by heat capacity. Constant volume, we have Cv delta T. Constant pressure, we have Cp delta T. Okay. More commonly, we use NCVM delta T. And here is NCPM delta T. What if we don't have CPM? We use NCVM plus R times delta T. Okay. So how do you calculate Q in isothermal reversible process? Okay. We don't have heat capacity for this process, but we can calculate if we know internal energy change. So next, all right, how to calculate internal energy change? For constant volume, no work. So the first law says internal energy is heat, which is Cv delta T. And then we showed that if it's ideal gas, then internal energy is a function of temperature and only, and so this equation applies to all process. Whether it's constant pressure, it's still CV delta T. If it's isothermal reversible, it's still CV delta T. But because delta T 0, if it's isothermal, okay, delta T 0, and therefore delta U is 0. Okay, now go on to the delta H. So to calculate delta H, we choose constant pressure. All right, because under constant pressure, enthalpy is heat, which is Cp delta T. And then we show for ideal gas, this equation applies to all process. So constant volume, you calculate by Cp delta T. Isothermal reversible is still Cp delta T, but delta T is 0, and therefore delta H is 0. Okay, so now let's go back to heat. How do you calculate heat for isothermal reversible? Using first law, we know work, we know delta U, so delta U minus W, that gives you positive nRT, ln V2 over V1. Here's a simple question you have seen twice, and you should be able to calculate Q, W, delta U for each step. But this time we want to add delta H. How do you calculate delta H? Let's go over each of them. Let's briefly go over the steps for the calculation. The detailed calculation you can find in the next few slides. Calculate the pressure, constant pressure, calculate work. Constant pressure is negative P delta V. Constant volume 0. Isothermal reversible negative nRT ln V2 over V1. So that's for work. For internal energy change, for heat, constant volume, they are the same. So constant volume, work, heat, both are CV delta T. Okay, because delta U equals Q. All right, and the equation to calculate delta U, CV delta V applies to all process. So for the third step, delta U is also CV delta T, but delta T is 0, and therefore delta U is 0. For the first step is also CV delta T. All right, and you should calculate delta T first. Use ideal gas law, you will see in the next slides, okay, to calculate delta T. And then you can calculate delta U, all right? And how do you calculate the Q? Well, for the third step, you already know W, you already know delta U, so you can use the first law, all right? Q equals negative W, because delta U is 0. And for the first step, also first law, Q equals delta U minus W. Okay, that's one way to do it. Another way for the first step is because it's a constant pressure, heat can be calculated by Cp delta T. Okay, so NCPM delta T to calculate the Q, which is also delta H, because constant pressure, delta H equals Q. Okay, now what if we don't have CPM? Because in this case, CVM is given. You can calculate the CPM by CVM plus R first, okay, and then you can calculate Q. Now, second step, delta. How do you calculate the enthalpy change? Same equation, CPM delta T, okay, CPM delta T. So calculate delta T and then calculate the delta H. Similarly, the last step, CPM delta T to calculate delta H, as long as it's ideal gas. And delta T is 0, so delta H is 0. All right, so that's the idea how to calculate each step. The detailed steps you will find in the next few slides, and I suggest you to try yourself and then compare with the answer keys. Here's a detailed calculation of the first step, and I suggest you to try before you look at the answers. And I want you to know that in physical chemistry calculation, there are many times you may find different ways to solve the same problem. All right, this is fine. As long as you use correct equations, eventually you should get the same answer. So here is the second step, and this is the third step. Okay, please try it, and if you have a question, please ask me. Before we end this section, let's introduce a new process called adiabatic expansion. Adiabatic means no heat. Okay, so if Q is 0, according to the first law, delta U equals W. Okay, so if system do work, it must consume internal energy. All right, if it's expansion, work must be negative. So a negative work means a negative internal energy. Internal energy change is CV delta T. So if delta U is negative, that means delta T is negative. Delta T negative means temperature decrease. So when a gas expands, its internal energy is reduced. The temperature falls. In other words, when gas expands, it do work to the surrounding by consuming its internal energy. So the temperature will decrease. It's a cooling process. Now this diagram compares isotherm with adiabatic cooling curve. So here, that's the isotherm. So all points has the same temperature. Now if we start with the same condition, initial condition, and both expand, one is isothermally, one is adiabatically, we just show that if it's adiabatic, temperature will decrease, and therefore the final point should be below the isothermal condition, expansion, because the temperature becomes smaller. But how much does temperature decrease? So we're going to derive equations in the next few slides to describe adiabatic process. So here is a adiabatic expansion cooling process, and because Q is 0, so delta U equals dW. Now delta U is calculated by CV delta T for ideal gas, and the dW is calculated by negative pressure times volume change. Now usually you use P external pressure, negative P external pressure times volume change. Now if this process is reversible, then the external pressure equals pressure, so we can just write negative pressure times volume change. Okay, so we have now this equation, CV delta T equals negative pressure times volume change. Everything belongs to the gas phase. Okay, so the pressure of the gas, the volume of the gas obeys ideal gas law. Okay, so P equals negative nRT over V. So plug in here. So we have this equation, CV delta T equals negative nRT ln V divided by dV. Our goal is to derive an equation to relate pressure, volume, temperature. So we need to remove the dV dt, and the way to do is to integrate. But in order to integrate, we have to separate variables, because on the right side we have temperature, we have volume, two variables you cannot integrate. So we can move temperature to the left side by dividing by temperature on both sides. So what we have now is CV divided by temperature dt equals negative nRV dV. Okay, so now on the left side only have temperature, on the right side we only have volume, so we can integrate like this. Okay, CV over T dt left side, right side is nR over V dV. Okay, note that CV is a constant, NR is a constant, so we can move out of the integration. So here this becomes CV, this becomes NR. And if we divide by NR on both sides, so this cancel, this comes here, all right? And if we define this as a constant C, because everything is a constant, we just use one constant C to represent all constant. Then we have C times integration T dt equals negative integration V dV. All right, so we know in math integration of 1 over x dx equals ln x, and therefore the left side will be C times ln t equals negative ln v. All right, now don't forget that you have initial to the final, so here you have C ln v ln t2 minus ln t1 equals, the right side should be ln negative ln v2 minus v1, but because it's negative, so you use ln v1 minus ln v1 ln v2. Okay, now ln t2 minus ln t1 you can write as C ln t2 divided by t1. The right side is ln v1 v2. Now C times ln can goes to the power. Okay, so you have t2 divided by t1 to the c's power equals v1 divided by v2. Okay, and if this ratio are the same, then cross multiplication will be the same. So that means v2 times t2 to the c's power equals v1 times t1 to the c's power. So that's give you the final equation like this one. So so here we use initial and final. You can use also use 1 and v1 and v2. So initial initial t initial to the c's power equals v final t final to the c's power. So this is an equation applies to reversible adiabatic expansion. Okay, we have learned Boyle's law, Child's law. Now we have one more equation, but this equation only for reversible adiabatic. So we just derived the equation for adiabatic reversible process. That is, volume times temperature to the c's power is constant, whether initial or final they are the same, in which C is a constant that equals the molar volume heat capacity divided by R constant. So if we use ideal gas law to replace temperature by pressure volume, all right, using ideal gas law, then we can derive this equation. Pressure times volume to the gamma's power. Note that temperature is replaced by pressure and the volume. So we don't have temperature in this equation. PV to the gamma's power, initial equals final. The gamma is the ratio of constant pressure heat capacity divided by constant volume heat capacity. Okay, so in summary, for reversible adiabatic process, okay, we have two more equations. It can be pressure volume to the gamma's power is constant, or volume times temperature to the c's power is constant. Okay, now compared to the Boyle's law. Boyle's law is PV is constant, and this is only for when temperature is constant. Then PV is constant. Here, for adiabatic reversible process, PV you need to raise to the gamma's power. That will be constant. Okay, so if you have a reversible adiabatic process, then you not only you can use ideal gas law, you can also use these two equations. for calculations of volume, pressure, or temperature. Sample question. When a sample of argon at 100 kPa expands reversibly to twice its initial volume, okay, so that means V final is twice V initial. What is the final pressure if the process is adiabatic isothermally? Okay, so first let's look at the adiabatic process. Adiabatic process, we have two equations. Okay, adiabatic reversible. Okay, two equations. We choose the one that have pressure. So PV to the gamma's power, initial equals final, and therefore we can calculate the final pressure. Okay, the final pressure equals initial pressure times initial volume divided by final volume to the gamma's power. Now, because final volume is twice initial, so we have 1/2. All right, gamma is 5/3. That is given. Okay, and the answer is 31.5 kilopascal. So that's the final pressure here. Now, isothermal, you use Boyle's law. So PV initial equals PV final. Okay, so we can calculate the final pressure. This is again 1/2. So you get 50 kilopascal. So right here. So you can see adiabatic process, the pressure decreases more quickly from 50 of the isothermal to 31.5 of adiabatic. And this is because adiabatic process consumes internal energy when it's expanded, so temperature drops and therefore pressure decreases more quickly.